So let's begin with blocking assignments, right? So what does the blocking assignment is? It will execute the statements inside the sequential block in the order that are specified. What I meant for a sequential block is there are actually two different blocks. I haven't discussed this sequential block and parallel block. I will discuss about these things in the next session, but right now just think there are two different blocks. The blocks that are inside begin and end, we are using this so far, right? Begin and end. The statements that are inside this will execute sequentially. That is why it is called sequential block. Whereas in parallel block, you can use statement like fork and join. In this, the statements that are inside this will execute parallelly. So as of now, we are only seeing sequential block. Inside the sequential block, the blocking statements will execute in the order they are specified. Like if you specify y is equals to 1 first and then z is equals to y. So first it will execute y is equal to 1, then it will execute z is equals to y. So they will follow the sequential order that are they specified inside the blocking statements. Okay, I will discuss this parallel block and sequential block and how they are different in the next session. Right now, the main purpose of blocking assignments is they will execute in the order they are specified, and they will use a symbol called is equals to. Okay, and for non-blocking statement, the symbol is less than equals to. We'll see how the non-blocking statements will work in the next slide. But in this slide, we will concentrate on how to use the blocking statements inside any always or initial block. So let's take an example. With the example, it will be very clear to you what does the blocking statements will do to your blocking assignments, right? So let's take an example. I'm defining different registers like this. We need to define only registers, right? Because these are procedural assignments. We have to use registers. We cannot use wires. So I'm defining three 1-bit registers like X, Y, Z, and then I'm defining a vectors of, let's say, 8-bit vectors, register A, comma register B. Okay, and I'm defining an integer also for a uh, I'm defining an integer. Just say, let's say, integer count, right? So we have defined different kind of data types like register 1-bit data type and register of a vector and integer. So in these three different data types, let's assign in initial block. Let's say initial, we are using sequential block because we are using begin and end statements. So this is called a sequential block. Inside the sequential block, I am assigning my x is equals to 0, y is equals to 1, z is equals to 0, right? I can do 3 in a single line by terminating with semicolons, right? Or I can write 3 different lines also, it doesn't matter because the semicolon terminates the statement. And then I'm using my count is equals to 1. Initially my count is equals to 1, I'm assigning. Then I'm assigning some register A is equals to my 8-bit hexadecimal of AA, and then my register B is equals to my 8-bit hexadecimal of 1, 2, let's say, right? So I have assigned all the data types till now. Then after some 15 nanoseconds, I want my register A to be A of second bit to be 1 tick binary 1, and I want after 10 nanoseconds my register B. This is called bit select because I'm only selecting the bit. Now let's say I want to do a part select like 4 down to 2. I'm selecting part of the vector which is 4 down to 2, and I'm assigning it to a 2-bit value like this. This is 4, 3, 2. So it is a 3-bit value of, let's say, 0, 1, 0. Okay. So after this, let's say I want my count is equals to count plus 1 without any delay. See, these are the different statements, blocking statements, right? Because I have used only is equal to symbol. So these are called blocking assignments. So let's see what happens with different time axes. So there is no delay for these things, right? So ideally what we'll think that all these things will execute, even this has no delay. So 1, 2, 3, 4. These 4 lines will execute at time t is equals to 0. But it is not the case, because the purpose of blocking statement is it will block each line before executing the next line. So first it will execute this line, then it will execute this line, then it will execute this line, then it will execute this. Not it will go to this line, right? Even though the delay is 0, it will execute up to this line at time period 0. So at time t is equals to 0, all the 3 lines 1, 2, 3, these 3 lines will execute up to, from x is equals to 0, y is equal to 0, z is equal to 0, and count is equals to 1, and these two. All these initializations will happen at time t is equals to 0. Okay. After this, in the sequential order, which statement is coming? This statement. So after 15 nanoseconds, this register A second bit will be initialized to 1. Okay. After executing this statement, it will go to next statement. So how much time it will take? 15 plus 10. This is 0. At 0, all these things are executed. So 0 plus 15, this line will execute. And 0 plus 15 plus 10, which is 25 time units, this statement will execute. Register B of 4 down to 2 is equals to 3 bit binary 0, 1, 0. So the 4 down to 2 bits will be assigned to this value. Then after 25 nanoseconds, we haven't given any delay here. So 25 plus 0, which is again 25. So at 25 nanoseconds, both register B will be assigned as well as my count will be count plus 1. Right? This is very, very important. Ideally, if you see, we'll think that all these statements without delays will execute at time is equal to 0. But that is not the case, because inside the sequential block, this is the sequential block, begin and end, the order of the blocking statements will execute in the order they are specified. Okay. So this is an example of blocking statements. I hope this will clear your doubts about blocking statements. Okay. So the purpose of blocking statements is it will execute in the order they are specified, but not the time delays, right? Even though the time delays is 0, this count will execute only after executing this all the previous statements with their assigned delays. Okay. Now let's see what is non-blocking assignment, right? The purpose of non-blocking assignment is it will execute concurrently, even though inside the sequential block, inside the begin and end block, all the statements will execute concurrently if you use this symbol, less than or equal to. Don't confuse with the logical operator less than or equal to. Whenever it is a inside the sequential block or always or initial block, this less than or equal to symbol will be a non-blocking assignment. So let's take the same example that we have taken inside the in the previous slide, and we'll do the same example here also to check how the non-blocking assignment is different. We'll take the same example, same registers. We have taken 3 registers X, Y, Z, and then 3 8-bit datas vectors, which is register A, comma register B, and we have taken what else we took? We took an integer count, right? And then we started initial block, initial, begin. Inside the begin, what we did? We initialized x is equals to 0, y is equals to 1, and z is equals to 0. And then we initialized register A. We initialized uh, count is equals to 1 first. So you can write count is equals to 1 also here. Count is equals to 1. Then we initialized register A and register B with some 8-bit data. I am writing some any data you can initialize. Register A and register B with some 8-bit data. Okay. After this, let's change these two statements that we have defined here from blocking to non-blocking. Okay. So let's do the second bit assignment as a non-blocking. See, I'm using less than or equal to symbol instead of equal to symbol, and I'm assigning it to a one tick binary 0. And similarly, I'm using my register B assignment from 4 down to 0 as a non-blocking. See, I'm using non-blocking statements as a 3-bit binary 0 1 0, right? Then I have used count is equals to count plus 1, and I'm ending my initial block. Now let's see what happens if you use the non-blocking statements, non-blocking assignments inside your sequential block of initial. So again, we'll draw time axis. So what happened? As we have seen, the non-blocking assignments will execute concurrently, but not sequentially. So what happened? At time is equals to 0, again at time is equals to 0, all these things will execute, right? Since they are non-blocking, it won't block the this count statement. This is very, very important. Since these two are non-blocking, the purpose of non-blocking statement is it will schedule the statements for a particular time period, but it won't wait for that much time period. In the case of blocking statement, it will sequentially it will go and it will wait for amount of time period that you have specified. But in the case of non-blocking, it will just schedule, okay, I have given a 15 time units delay, so execute this statement at 15 time delay and execute this statement at time 10 time delay, right? But it won't wait for 15 nanoseconds or 10 nanoseconds. So the order is like this: at 0 time period, all the statements x is equal to 0, x, y, z, count, register A, register B, even count is equals to count plus 1 will also execute at t is equals to 0. All these three as well as this. Okay. And then it won't go to 15 nanoseconds because 15 is larger than 10. So it will go to 10 nanoseconds because I have already scheduled that this statement should be executed at 10 nanoseconds. It is not like waiting for 10 nanoseconds. It is scheduled at 10 nanoseconds. This is the primary difference that you need to understand. It is not waiting for this much delay. It is scheduled at this delay. So at 10 nanoseconds, my register B will be executed, and at 15 nanoseconds, not 10 plus 15, because it is not adding to the earlier time period. It is just scheduling. So at 15 nanoseconds, my register A will be executed. Right? See, this is the main difference. In the case of blocking statements, it took 25 nanoseconds to perform these things. I'm not comparing in terms of time delays, but I'm just telling in the case of blocking statements, it will execute sequentially and then it will add to the previous time period. After it will wait for 15 nanoseconds, if you give 15 nanoseconds, and then it will add 15 plus 10 to execute the next statement. But in the case of non-blocking, it will just schedule the time periods, but not wait for that time period. So at 10 nanoseconds, the statement will execute, and at 15 nanoseconds, the statement will execute. It will just schedule, but it is not waiting for 10 or 15 nanoseconds to pass. Okay. So this is the use of non-blocking statements. In these statements, in this example, I have used both blocking as well as non-blocking in the same initial block. But this is not recommended. Always use either blocking or non-blocking because it will be confused if you use both the statements. You don't know the order of their appearance. So it is always preferable either you will use blocking or non-blocking. It is not a mistake to use blocking statements. Blocking statements has its own purpose and non-blocking statements has its own purpose. We'll see once we see the examples of blocking and non-blocking. So let's take a application where the non-blocking statements, non-blocking assignments are used. Usually the non-blocking assignments are used to model several concurrent data transfer that takes place after a common event. You have a common event, let's say my clock is turning from 0 to 1. At this particular common event, let's say same example we'll see. If you want to execute all these three data statements at the same time period, you can use non-blocking assignments instead of blocking assignments. Okay. So that is the purpose of non-blocking assignments. Let's take an example of non-blocking assignments. Let's say I have always, as I'm saying, always at the rate of pausage clock. I will explain what is this pausage clock in the coming slides. Always at the rate of pausage clock. I want these three different statements, like I'm beginning, I'm assigning my register 1 less than or equal to, because it is a non-blocking assignments. I'm assigning my register to 1 and register 2 to a event of negage clock. I'm assigning it to, let's say, input 1 and input 2. I will explain what does these statements will do. And let's say my register 3, again the non-blocking. Let's say at time 1 nanosecond, I want register 1. So what is happening here? Even though they are inside the sequential block, since we have used non-blocking assignments, they will all try to execute at time t is equals to 0. So that is what concurrently, they will all execute concurrently. But since there is a time period of 1 nanosecond delay, so let's begin with this statement. First, it will execute register 1 is equals to 1 tick binary 1 at time t is equals to 0. At the same time t is equals to 0, it will execute this statement, but it will execute this operation in and into. It will only assign it to register 2 when this event is happening. What is this event? At the rate of negative edge of clock. When there is a negative edge of clock, then only it will assign this to register 2. Similarly, it will execute register 1 data, whatever you can give data or expression here, it will execute, let's say, negation of register 1. It will execute this statement at time is equals to 0, but it will wait for this 1 nanosecond or 10 nanosecond, whatever delay you will give, it will wait for that much amount and then it will assign to register 3, right? So what is the purpose here is, it is eliminating the race condition. We will see the race condition in the next example. So let's see the purpose here. So what happens here is, the data of register 1 is initially copied to a temporary variable and it is stored in a temporary variable. And then after the particular amount of delay you have given, that data inside the temporary variable will be given to register 3, but not the data that is currently present in the register 1. This is very, very important. It looks confusing, but you need to understand this. What is happening inside the non-blocking statement is, the non-blocking assignment will always read the right hand side expression. So it will read the right hand side, whether expression or register, it will read it and it will perform and it will store inside a temporary register. Then after particular amount of delay, if you have given delay, it will execute after particular amount of delay. If you don't specify any delay, immediately it will store the data here. Okay. Since you have specified some amount of delay, so it will wait for that amount of delay and then it will place the data that is already present inside the temporary variable inside the left hand side variable. So this is very, very important thing of the non-blocking assignment. We'll see what is its application. The primary application of non-blocking assignments is elimination of race condition. So first of all, we'll see what is a race condition. A race condition will happen when you want to swap data between two different variables. Let's say I have a two buckets and I have a ball of A here and a ball of B here. So this is bucket 1, this is bucket 2. So I want to swap B to A as well as A to B. So how to do that? If you want to do both at the same time, what happens? You lift this ball and you lift this ball at the same time, and you cannot place them at the same time because there will be a race condition happening. So how to eliminate race condition? By simply taking one more bucket, temporary bucket. So place the B ball here and place the A ball inside the bucket B, because B is already empty here, so A is coming here. So this block is empty. Now place this inside this A bucket 1, right? This is the sequence of order you follow to eliminate the race condition. So if you use the blocking statements, it will create a race condition because the blocking statements will execute at same time period, right? And they want to execute both at the same time period, so it will create some race condition. Let me take an example, then it will be very clear to you. So let's take a non-blocking and blocking assignment of this swapping thing. So first of all, I'm using an always block, always, let's say at the rate of passage of clock. I'm using two different always blocks. First one is A is equals to B. Similarly, I'm defining one more always block, same at the rate of passage clock. So this is my event. I will explain what is an event. The event is here is passage of clock. At this event, I'm executing A is equals to B and B is equals to A. I'm using blocking assignments, right? So we'll see what happens if you use blocking assignments. And this is one method of doing, and the other method of doing is I will use non-blocking assignments. Same at the rate of passage clock, I will use non-blocking, which is less than or equal to symbol. Similarly, always at the rate passage clock, I want my B to be A, right? So what happens if you use blocking statements? The A and B, since we know all the always blocks will start at time t is equals to 0, right? We have already known that all the always and initial blocks will start at time is equals to 0. So at time is equals to 0, A wants to get the B value as well as B wants to get the A value, right? So we don't know what value it is getting settled. It depends on the Verilog simulator. Let's say this statement is executing first. We don't know which one will execute because we are specifying both should execute at time t is equals to 0. And let's say this is executing first. So what happens? My B is equals to A. So my A value will be stored inside B. And after this, let's say this statement is executing. This is executing at first and this is executing at set, but both of them are executing at time t is equals to 0, right? So what happens? My B is already become A and that A will be given to again A. So both A comma B will be now A's, right? This we don't want. We want A and B to be swapped. But what happening here? Both A and B are storing same value. Both A and B are storing both A because this statement is executed first. But let's say this A is executed first. In this case, what happens? My A will become B. So my A will become B first, and then that B will be assigned to B. So my A comma B will be now both are B's. Again, this is also wrong, right? Even if this executed first or this executed first, it doesn't matter. At the end, both are getting same values if you use the blocking statements. So this is called race condition. You are not actually swapping the data, you are storing the same data twice in both the registers. This we don't want. How can we eliminate the race condition? We can eliminate by using non-blocking statements like this. Now let's see what happens inside the non-blocking statement. Inside the non-blocking statements also, both of them will execute at time t is equals to 0. But the nature of non-blocking statement is it will first read the data, right? So it will first read this data B inside some temporary variable temp1 is equals to B. So temp1 it stored B data inside temp1. Similarly, this will also execute at time 0 and this data A is stored in temp2, right? First the read operation is happening. Since there is no delay, we haven't given any delay. After the read operation, what happens? Whatever the value that is stored inside the temporary register will go to A. So since here the data stored is B, so A will become B, right? A will become B, and at the same time my B will become A. So this A is coming not from A but from temporary variable. This is very, very important. This A is coming from temporary variable 2 and this B is coming from temporary variable 1, right? By this way, you can swap A and B by using non-blocking statements. Here there is no race condition because A and B are easily swapped because we have used non-blocking statements. How it is done? Since the non-blocking statement do two steps instead of single step. In case of blocking step, both read and assign, read and write, I can say read and write will happen in a single step. But in case of non-blocking statements, first it will read the content of the right hand side and put it inside some register or temporary variable, and then it will try to write that data which is stored inside the temporary variable inside the left hand side of the expression. So this is very, very, very important feature of the non-blocking assignment, right? So let's see how to do the same operation of swapping by using blocking statements. So how to do that? So I'm erasing this side of the content. So with uh, with non-blocking, it is clear, right? We don't need to write any temporary variables because the non-blocking itself will use the internal temporary registers and store the data of the right hand side in the read phase. Think like this, the non-blocking has two different phases. First phase is read phase and the second phase is write phase. In the read phase, it will read the data of the right hand side and store it into some other variable, and then in the write phase it will again get the data from the stored temporary variable but not the actual right hand side read variable, right? So how to do the swapping using blocking statements? We saw if you write like this, the blocking statement won't execute swapping. It will create a race condition and then it will store the same data twice. So we don't want this. We want to swap by using blocking statements. So how to do that? I will write a single always block at the rate passage clock. Okay. In this, again I am defining begin. So what is the advantage of non-blocking statement? Non-blocking has two different states, right? First phase is read and next phase is write. So similar thing I am doing using blocking statements. First phase is read. So I am commenting this, double quotation means comment. Read phase. In read phase, I want my temporary 1 is equals to A and my temporary 2 is equals to B. I am using two different temporary variables to store A and B first. After read, I will write. In write phase, I want my B to be temporary 1 and my A to be temporary 2. Then N. Now see what happens. Even though we are using the blocking statements, right? We are using the blocking statements. We are not using less than or equal to, which is a non-blocking statement. We are using the blocking statements and we know always block starts at time t is equals to 0. And then in the sequential block, they will execute in the order they specify. So first A will be stored in temporary 0. All are executing at time t is equals to 0 because I haven't defined any delay, right? So all of them will execute at time t is equals to 0. At t is equals to 0, what happened? My A will be stored in temporary 1 as well as my B will be stored in temporary 2. At the same time t is equals to 0, my B will be having data from temporary 1 and my A will be having data from temporary 2. See, the blocking statements also you can do the swapping operation without adding any delay. We haven't added any delay, but we have added two extra temporary registers, right? So that is how you can do the swapping of two different variables using blocking statements also. So if I summary this thing, so what is the summary I got from this blocking and non-blocking statements? First one is the non-blocking statements, use of non-blocking statements is highly recommended, right? Because we have seen the blocking statements will cause race condition. We thought that A is equals to B and B is equal to A will swap, but it is not swapping, right? So always prefer non-blocking statements. inside the sequential blocks. And the second thing is, the purpose of non-block statements is you can use it for pipelining operations or modeling of several data types that are occurring concurrently. So that is the purpose of non-blocking statements. And the third conclusion we can make is the non-blocking statements will consume more memory because it is having a read operation which will take two extra temporary registers. So this is a drawback of non-blocking statements. What is the drawback? It uses more memory because it will require some temporary variables like this. But the advantage is you can eliminate the race condition as well as you can use the non-blocking statements for pipelining or concurrent operations. What does pipelining means? In the computer organization, you must have learned these terms like in order to execute any statements, the cycle of execution is three different phases, right? What are the three different phases? First phase, it will fetch FETCH, it will fetch the statement, and second stage it will decode, and then third it will execute, right? So this is called the cycle of operation in computer organization. You can use pipelining. In one stage it is fetching, then in the next stage it will decode, in the next state execute. So you can use pipelining technique to merge these three things in two different ways. Like if the first register is fetching, use the second register for decoding and use the third one for executing. So at this time this will fetch, decode and execute. At this time it will execute. At this time, it will again fetch the next statement. So this is called pipelining architecture. You will understand pipelining architecture once you complete the computer organization course. But the non-blocking statements will be used for this kind of architectures where you can perform pipelining as well as concurrent assignments. Okay. Thus, this is all about the non-blocking statements. Once we have learned how to use the initial and how to use the always and how to use the procedural statements like blocking and non-blocking. Now we want to see how to use the timing control inside the behavioral statements. As you can see in the Verilog, all the statements that are executing at time t is equals to 0 unless and until you specify any delay, right? So in order to proceed the Verilog coding to next time period, you need timing control, right? Otherwise, every statement will execute at time is equals to 0. If you want to execute step by step, you will have timing control. So the timing control can be done by using three different things. One is delay based timing control. Second one is event based timing control. And third one is level sensitive timing control. So we'll explain one by one. So why do we require timing control? If you don't have timing control, your Verilog code will not proceed in time, right? It will stop at particular time. So in order to have the Verilog code to proceed, we will have timing control statements. So let's begin with delay based timing control. So what does this delay based timing control will do? It will execute the expression after certain amount of time period that we have specified. Till now we are using this statement, right? So whatever the expression that is there here, it will execute after particular amount of time that you have specified. The time can be specified by using either number like this or an identifier or min typical max expression. We have seen this, right? In the gate level modeling, we have drawn like this 4 is to 6 is to 5. So minimum, typical and maximum. You can use either this for timing control or simply you can use a simple number or you can use an identifier. We'll see an example, then it will be very clear to you. And there are three different ways that you can define the delay based timing control. One is regular delay control, second one is inter-assignment delay control, and third one is zero delay control. So we'll see one by one in the coming slides. So let's begin with regular delay control. So I am taking I'll try to explain all the three different things like how to give the timing using number or identifier or min max type, min typical max type expressions. So in this example, I'm taking, let's take a parameter to get the identifier. Instead of number, you can give any identifier like this parameter, let's say my latency, latency, right? Latency means the amount of time period it will take to perform any operation. It is like a delay only. Latency of 20 nanoseconds, and let's say my parameter of skew is equals to 2 nanoseconds. My skew will be like this. I mean, if the latency is 20 nanoseconds, the skew is extra time period that it is having. Okay, I'm defining two different parameters, latency and skew. Let me erase this. I need to use semicolon to terminate these two parameters, right? And then I'm defining some registers X, Y, Z, P, and Q, right? Now I am doing initial, begin. Now let's see how to use the regular delay control. We are using it from the beginning of this course, but we don't know that its name is regular delay control, right? We will see what is the regular delay based control. First, my X is equals to 0. There is no delay. Now, if I want a delay of 10 nanoseconds, my Y is equals to 1. So, this is called regular delay control. We are using from the beginning of this course, but we don't know its name is regular delay control. This is called regular delay control. Here, I am using directly a number. You can use a identifier also like this. Let's say latency, the same name, latency, I am giving here latency. After some latency, here I am defining Z latency is equal to 20. So, after 20 nanoseconds, the Z will be executed to 0. Okay. Then either you can give directly the parameter number parameter, or you can give expression as well like this, latency plus some skew. After latency plus some skew, my X is equals to 1. You can define like this. So what does it do? It will add 20 plus 2, and after 22 nanoseconds, it will execute my X is equals to 1. Okay. Now let's say I want to define this min max typical expression. So how to do that? I can do like this, asterisk 4, 5, 7. So this is my minimum delay, this is my typical delay, and this is my maximum delay. I'm assigning my Q is equals to 1 tick binary 1, right? And so these are the different ways you can define regular delay control. First one is by using a simple number, and second one is by using the identifier, and third one is by using min, typical, max expressions. Okay. And the second kind of delay based control is intra-assignment delay control. What does this intra-assignment delay control is? Previously, what we did, we have defined first delay and then we have written the expression or statement whatever we want, right? But in the intra-assignment delay, we can define like this. Let's say my X is equals to 0 and my Y is equals and my Z is equals to 1, and my Y is equals to, after 5 nanoseconds delay, X plus Z. So what does it do? First it will execute this, and then it will wait for 5 nanoseconds delay, and then it will post the data inside Y. So this is called intra-assignment delay. The same thing you can visualize like this. You have X is equals to 0 and Z is equals to 1, and my temp of XZ is equals to X plus Z, and after 5 nanoseconds delay, my Y is equals to temp of XZ. So these two things are same. Here I am reading this data, and then after 5 nanoseconds I am storing it to Y. But here, first of all, I am performing the operation, and after 5 nanoseconds I am performing this assignment. Both the things are same, right? So what is the difference between these two things? Let's say here, if my X and Y are changing before the 5 nanoseconds, what happens? It will not execute the changed value, it will execute the previous values what are there in the X and Z, right? So it will execute the previous values of X and Z, and then it will wait for 5 nanoseconds, and then it will store into Y, but it will not take the present values, right? But if you write an expression like this, asterisk 5 Y is equals to X plus Z. So what is the difference between these two things? Here I am defining delay first and then assignment later. So what does it do? After 5 nanoseconds, whatever the data present at x and z, the present data, it will sum and then it will post inside y. But in this statement, what it will do? It will execute this x plus y at time t is equals to 0, and whatever data at time t is equals to 0 it will do, then it will wait for 5 nanoseconds delay and then it will assign the expression x plus z that was executed at time t is equals to 0 inside this y. So this is the basic difference you need to understand, intra-assignment delay as well as regular delay. Okay. Now let's see what is zero delay. A zero delay is nothing but delay of 0. Why do we require zero delay? Let's say we have seen inside the initial block, if you have multiple statements like this, x is equal to 0, y is equals to 1, z is equals to 0, all these statements will execute at time t is equals to 0, right? But you don't know in which order they are executing, but they will execute at time t is equals to 0. If you want to specify, I want to execute my z is equals to 0 in the last of time t is equals to 0, then you can specify as 0. So this z is equals to 0 will definitely executed in the last compared to y is equals to and x is equals to. So these two things will also execute, these three things will also execute at time t is equals to 0, but this will execute last. Okay, that is the purpose of zero delay control. Usually we don't prefer this, but you should know what is the zero delay control also. So let's take an example of what happening. Let's say I have a initial begin x is equals to 0, y is equals to 0, and then similarly I have one more initial block. I'm beginning, I'm using 0 delay of x is equals to 1 and 0 delay of y is equals to 1 n. So ideally these two initial blocks will start at time t is equals to 0, and ideally both are having 0 delay, they both should execute. But since we have used hash 0, so this will execute last, so finally my x will be 1 and my y will be 1, because this will be executed, but this will be replaced with the latest statement of x is equal to 1 and y is equals to 1. This is the purpose of zero delay. So you can tell which statement to be executed finally. Usually we don't prefer this, but you should know the concept that it is existing in Verilog. There is a concept called zero delay control. Okay. So this is all delay based timing control. Now let's see what is an event based timing control, right? So we'll see what is an event based timing control.